We'll be starting in about a minute. Okay, let's go ahead and get started. In order to get attendance, I'm going to have you do, some of you are going to have to do a kind of attendance SWIC afterwards. It's not hard, it's just over what we're going to talk about today. So for those that have to do it, it's not a big deal. It probably takes about 5-10 minutes or so. But you'll need a code to get into it, and I'm going to be giving you that code in pieces. So there's 9 digits in the code. And I'm going to go ahead and give you the first 3 digits here in a second. But the first thing I need you to do is go ahead and type in your name, your full name, your given name and your surname into the chat. And I'm going to be asking you to do that several times. And if there's any time that you're not doing that when I ask you to, then of course that means you're going to have to do the SWIC. That's one of the conditions. Okay, so the first 3 digits of the code, so you might want to write this down, is the number 2, lowercase t, and then the number 2 again. So 2T2. Okay, so we're going to be whiteboarding worksheet 6. Worksheet 6 will not be on not tomorrow, for you guys it's Thursday, will not be on your test on Thursday. Your test, since it's on Canvas, and I know it's a little bit difficult to sometimes have to type in your answers and kind of explain all your work and everything, I've made it 115 minutes. It shouldn't take anywhere near that amount of time, but since I don't know how long it takes some people to type in answers, I wanted to err on the side of caution. I also want to talk a little bit about what's happening with the AP test for the College Board. Right now, the College Board has decided that the test will just be free response. It won't cover units 6 and 7. Those are College Board units. Nothing says we have to do them in that order. In fact, most veteran teachers do not do them in that order. The unit we're doing right now, they actually consider unit 6. So this one will not be, unfortunately, on the AP test. The units that we have not done yet that will be on the AP test are units, what they call 3 and 4, or excuse me, 4 and 5. 4 is momentum, which is going to be the next one we do. That's not a concern. It's pretty easy. It doesn't take very long. Unit 5 is the rotational stuff. And we're not talking about uniform circular motion. We're talking with radians. And it's a little bit more concerning. I usually leave that to the very end because it's a good review. It actually covers everything. For instance, remember all the kinematics we've done with meters, meters per second squared? Well, there are angular kinematic equations that have radians, radians per second squared, but it's actually not any different than regular kinematics. It's pretty much the same thing. Instead of figuring out how far something moves, you're trying to figure out how many radians that it goes through. So that's why we use radians, radians per second squared. Same thing for energy. We had translational energy, 1/2 mv squared. Well, there's rotational energy, and the equation looks very similar. Just like there's linear forces, F equals ma, there's rotational forces, except we don't call them forces, we call it torque, but the equation looks similar. We haven't covered momentum yet, but there's angular momentum. So that's why most veteran teachers actually do the rotational unit last, because it's a good review. That's one I'm a little bit concerned about, because not that you won't know the stuff, it's just that looking at things in radians per second squared at first is kind of strange because you're not used to it. So what I've done is I went ahead and went into the AP Classroom, which I don't really like a whole lot, but I've opened up the review sections for all 1, 2, 3, which is stuff that you should know how to do already. I've also opened up for Unit 5, which is that unit that I'm a little bit concerned of. So you don't have to do it if you don't want to, but I've opened it up for those students who are maybe bored over spring break, since I know where you're going to be. You're not going anywhere, like I'm not. So if you want to do it, it's open. You don't have to, though, if you don't want to. Okay, so anyway, that's all that I know at this time about the AP situation. So what I want to do is I'm going to start looking at our answers for worksheet 6. This is looking at energy in a different way. Instead of looking at gravitational energy as mgh, we can't do that anymore because the force of gravity isn't constant. If you remember, for first semester, we always said the force of gravity is equal to mg because the gravitational field was pretty much constant. But we now know that if you move really far away from the Earth, that gravitational field is not constant. It's actually an inverse square relationship. And so that's what we're looking at. Again, this will not be on your test on Thursday. All right, so
Mr. Lenfestey, did you end up getting my worksheet 7 that you said you didn't get?
yeah, I got it now.
All right, cool.
Okay, so let's see. I think I'm going to go to Annie and Allie's folder here. And let me paste this in. And then I'm going to share my screen with you all so that you can see what I'm doing. Okay, so I'm just going to kind of pick whiteboards at random from different people who have sent it to me. So this is Allie and Annie's paper or whiteboard. This is for problem number 1. So we can't use MGH anymore. So the question is, how can we find, if we have this graph of force versus distance, how can we find the energy stored as gravitational? And they said, just find the area underneath the graph. And that's exactly right. So for instance, number 2, we're trying to figure out from 2 Earth radii to 3 Earth radii. So I'm going to draw on theirs. So 1 Earth radii is way up here. Here's 2 Earth radii, so it's right here. I think that's what the problem says. And then 3 Earth radii. I might be wrong about that, but it's the same general idea. And then 3 Earth radii is here. And so we're going to find the area. Let's see, I think I can draw. So imagine finding the area bounded by the curve. It kind of looks like a trapezoid. And so you can cut it into a triangle and rectangle, just find the area. Or if you know how to find the area of a trapezoid. So that's the next one. Thank you for that one. Let's see, let's pick a different group now. Okay, let's look at Dan.
Mine were just images, by the way. I didn't really, I just did it on paper and then I just took pictures of it.
That works.
Okay.
Okay. I wonder which one it is. It's probably this one. Oh, let's see if I can zoom in. How do we zoom in? Oh, down here. Okay, so for number 2 and number 3, Dan, did you just find the area of that area?
Yeah.
Okay.
The area underneath those two.
And I think that the formula you're using there is the area of a trapezoid. It's 1/2 the sum of the two bases times the height. And for number 2, he got 5.67 times 10 to the 7th, and that's what I got. And for number 3, same idea. The height would be the radius, which they give you up here in the problem. They tell you what the radius is. And he got 2.74 times 10 to the 7th. Both of those are joules, and that's what I got too. Okay, thank you very much.
Good stuff, Dan.
Thanks, big guy.
All righty, okay. Okay, then in number 4, what it wants to know is, how can we find out what is that area? Let's see if I can go back. So I drew a trapezoid, but I think if you saw that, it actually didn't fit this curve exactly. It was probably a little bit too much area. It was a little bit too big. If I want to find the area exactly, what I have to do is I have to integrate this equation up here with respect to r. And so it says now using calculus, derive what that equation to be. So let me go ahead and let's see, Adam, I think I'm going to pick yours now. This is number 4, 5, and 6. Okay, so when you integrate it, it's kind of hard to show all the steps for integration. So if somebody has a question on that, let me know. But when you integrate that, you end up getting this negative out front. So I want to focus your attention on that. It's kind of weird, but when you integrate that, you get negative gm. I'm going to make that one a big M because it's 2 different masses. Negative gm, big M, little m over r. Okay. Any questions on that one, number 4? Okay. Then number 5. So first, actually, before I move on, so compare that to the equation we've been using in energy before. We use MGH. MGH is a direct relationship, but this equation is actually an inverse relationship, and actually it's a negative inverse. So it's kind of weird. It's, in other words, it's below the x-axis or the r-axis or whatever. So it's kind of strange. Okay, then using that expression for number 5, what would the gravitational energy be at a distance of infinity? So imagine that you plug in for r here a really big number. That means this whole fraction would be a really small number because it's over a big number. And as that big number gets bigger and bigger and bigger, that fraction becomes smaller and smaller and smaller. In fact, it goes to 0. Nice. So number 6 is a little bit confusing. Let me explain it by trying to get you to remember. You remember, in fact, Adam, I think you did this for me. You remember we did the demo where I had the very large sphere and you put it up against your nose and you let it swing and then let it come back. Do you remember we picked the bottom of the swing to be the height 0, right? And so that's what this problem's talking about. So normally we pick the lowest position to be the height of 0. That's because with the equation MGH, you can pick your height of 0 wherever you want it to be. But that's not true with this new equation. It has a 0 value at only one location, and that location is at infinity. So the logical location is infinity. That is the spot. So it's weird because here's the thing that's weird about it. Usually when you're thinking about, okay, I'm going to lift up my calculator here and get higher and higher and higher, you're thinking the gravitational energy is increasing, and it does. But think about what the gravitational energy would be at infinity if I keep on lifting it up to infinity. It's equal to 0. So that usually causes lots of problems for students. They're like, wait a minute, I lift this up higher, it's getting bigger, but eventually it gets to 0. And here's the reason why. Do you see this negative out front? That's because right now it actually has negative gravitational energy. It's really low in the well. And what I'm doing is I'm lifting it up higher and higher and higher. It's getting more gravitational energy, but it's getting closer and closer to 0. I'm getting closer and closer to the top of that well. So that's the way you need to think of it. Okay. Nice job. Thank you very much, Adam. Okay. So the next one that we're going to do is on the backside, number 7. Okay, my guess is this one might have been kind of confusing for some people. Before I give it to you, though, before we start talking about it, I actually want to give you the next 3 digits and the code that you need, the access code to access the SWIC. Before I do that, though, again, with attendance, I need you to go ahead and type in your name into the chat. So if you can go ahead and do that, your first and last name.
So is the SWIC also required? I'm just curious because I thought the SWIC was
I
for that
will
unintended.
totally explain that at the end.
Okay.
Okay. The next 3 digits in the code are, these are all lowercase. Z, D, 1, number 1. So Z is in zebra, D is in dog, and the number 1. Okay, so. Okay, now we're going to look at number 7. Number 7 was looking at this rocket ship, trying to figure out what speed it would need. So let's see, I think I've used everybody that I had on here. So let's check email. Okay, so yes, the answer is correct there, but I think I want to go into a little bit more detail because I want to draw a picture here because I want to make sure people understand how to do this problem because it looks a little magical the way John has it set up here. So that's supposed to be the Earth, and now I'm drawing this rocket ship on the Earth. We're gonna make it black. And now, so that's the initial picture. The final picture is now my rocket ship is way over here. According to the problem, we're going to say it's way out in infinity. And we want to know how much speed it has initially here in order to make it all the way to infinity, just barely make it there. Well, in order to solve this problem, we have to use conservation of energy. Initially, at this initial location, it has gravitational energy and it has kinetic energy because it's lifting off. It's a rocket ship. It also has that gravitation. It has a gravitational energy way out in infinity, and it has some kind of kinetic energy. However, let's say it just barely makes it to infinity. If it just barely makes it to infinity, its speed is basically 0, runs out of steam. So that means kinetic energy is also 0. And if you remember the equation that Adam showed us, at infinity, the gravitational energy is also 0. So that means what I have is this initial energy, gravitational plus kinetic, is equal to 0. Which at first students are like, what? That's weird. That doesn't make sense. But if you remember, the equation for gravitational energy has that negative in it. So let me go ahead and fill this in a little bit. So this becomes negative GMM over R equals 1/2 times little m v squared. By the way, this little m, that's the mass of the rocket ship. The big M is the mass of the planet, whatever it is. So there's this negative out front, and so that means I can add that term to the other side, and that's the equation that we have shown up here that John shows us, okay? So I wanted you to understand that that's not magical where we got that equation at. It actually just comes from conservation of energy. And then the mass of the rocket ship cancels out, so it doesn't matter how big the rocket ship is. And for Earth, yes, I agree with him. It's around 11 kilometers per second. Nice. So, by the way, you can figure out what this escape velocity is for anything. You could find the escape velocity for our solar system. Mostly the mass of the solar system's in the sun. So in this equation that we have here, square root of 2gm over r, the m would be the mass of the sun. You could do it for, and by the way, that would be then the speed you need for a space probe to leave our solar system. Like for instance, the Pioneer or Voyager space probes that left our solar system in the early 70s. If you wanted to figure out what the escape velocity is for our galaxy, you could plug in the mass of the Milky Way galaxy to figure out, okay, what speed do we need in order to leave our galaxy to go to Andromeda galaxy or something. You could do it for anything. Okay, so thank you very much for that one, John. Okay, instead of going right to number 8, I want to make sure that we're covering, because it's going to take a little bit longer, I want to make sure that we cover 9, 10, 11, because people had problems on those on the last quiz that we had. So let me check somebody else's out. Okay, let's look at number 9. Okay, so yes, I like the way she did this here. The reason why I wanted to mention this problem is a lot of students on the quiz, they actually plugged in the mass of the Earth and the radius of the Earth, which is fine. I don't have a problem with it. I'm a little suspicious that you were able to somehow miraculously remember that number, but that's fine, whatever. Here's the reason why I think it's important that you don't do that. Notice that she did not do that in her solving here. She didn't plug in the mass of the Earth at 5.98 times 10 to the 24th. She didn't plug in what the radius was meters for Earth. All she did was plug in m over 10 because the mass is 1/10 that of Earth. And she plugged in 1/2 the radius because that's the radius of this planet. And so she has m over 10, and it should be divided by, I think we missed that here, divided by 1/2 of r, that whole thing squared. So really it's going to be 1/10 over 1/4. Well, that becomes 4/10. So 4/10 of the acceleration due to gravity on Earth, 4/10 times 10 gives you an answer of D. The reason why this is important not to memorize these equations and not memorize what the mass of the Earth is because you might not get a problem like that. Maybe you'll have planet X and planet Y. Planet X has a mass of m and a radius of r. Planet Y has a mass of 3m and a radius of 1/3 r. How does the acceleration due to gravity on Y compare to X? You might have to do stuff like that. And that's exactly how you would do it in this problem here. Thank you very much, Malia. Okay, the next one I'll look at is number 10. Number 10 is a similar one. So let me pick somebody else out. Maybe. Okay, so for this one, it says that on some planet, this object has a weight of W, and the planet has a radius of R. We're going to now pick this object up and move it a distance so it's now 4r from the center. Remember, the new equation for gravity is an inverse square relationship. So if you move it further and further away, the force goes down, but it doesn't go down just as a factor of r, it goes down as a factor of r squared. So if it goes to 4r, now it's going to be 1 over 16 r squared. So that's exactly what they did here, and they got an answer of E. It's 1/16 the weight. Nice. Okay, and number 11 real quick. Stop me if there's questions in any of this. Okay, number 16 or number 11, sorry. Oops, no, a different group. Oh, Jaden. Okay, so
Oh yeah, I just sent pictures of my work as well.
that's fine. All right, so we'll look at number 11 here. Okay, so uh-oh, I'm not sure if I can. Okay, I'm gonna have to zoom out a little bit. I don't know if you can kind of see it down here, but it looks like she has B. If you could look at your problem, it says that the mass now is twice the mass of the Earth. So if you got more mass, the force of gravity goes up. It's a one-to-one relationship. So that means it's going to be twice the amount of force. But hold on, it says now it has twice the radius. So that means it's going to be a inverse square relationship. So it's going to be 1/4. So it's going to be 2 times 1/4, which is 1/2. So it's going to be 1/2 of 500, which is 250. Nice, good. Okay, now let's see if we can go to number 8. Let's see, is there, oh, Kyler. Okay, this one was an AP problem, not that you're gonna see this one, unfortunately. But the first part is just simply kinematics, so D equals V bar T, and you're finding the radius, and we got an answer of 3.83 times 10 to the 6, and that's what I got. And then for part B, trying to find the mass, I set the net force equal to the force of gravity, big G M1 M2 over R squared, and solve for the mass of the planet. And they got 6.6 times 10 to the 23rd. That's what I got as well. Part C, calculate the total mechanical energy. For that one, we have to use that new equation for gravitational energy, negative Gm M over R. And then it's going to have also kinetic energy, 1/2 mv squared. We've already figured out the speed. So I just plugged in the numbers. I'm thinking I must have did something wrong because the other class also had a negative in the answer. I'm not sure why. I have actually, maybe I dropped off my negative. I had a positive that amount. I think I agree with your setup though here for energy. And so I just simply plugged in. I don't know, maybe I dropped off a negative somewhere. So you
I think
might
I had
want,
a negative too.
you had a negative, okay. Okay. And then part D says, if it is now placed in a lower orbit, would the orbital period be greater or less than? For that one, I think we've talked about this problem already, and this would be less than. And they said because the distance needed to travel is less. I added to that a little bit more for my explanation. I said that since the radius goes down, the speed goes up. And since the distance goes down, like they said here, the time must go down as well. Okay, and then part E says, what if it's not circular motion, but we have the thing in an ellipse? Can, you know, what would the new speed be? And at first you might be going, well, I can't solve this because it's not a circle. I can't use mv squared over r. You're right, you can't. But you can use conservation of energy. And so, in other words, it tells you what the speed is and the distance at closest approach. So you can use EG plus EK equals later on EG plus EK and then plug in. So I'm not sure. Oh, wait a second. You did angular momentum conservation. Maybe. Must have looked this up online. Maybe you can do it that way, but that's not the way I would do it since we don't know anything about angular momentum.
I didn't really know how to do it, and so I had asked my brother and my friend how to do it.
Okay. So I would, does it make sense, Kyler, of just using energy conservation, EG plus
Yeah,
E?
it'd
Okay.
probably be a lot easier.
Okay. And I do get an answer that's pretty close to that. I got 3,394 meters per second. You probably could do angular momentum once we learn about angular momentum. That's a neat thing about the AP test is there's more than one way to get the answer. And I like to stick with energy because it's usually kind of easy to do. All right, I need to give you the last four, I think, digits, or excuse me, last three digits, don't I? Yeah. Okay, so let me stop sharing here. Before I give you those last three digits, can you again, for attendance, type in your name, your first and last name, please, into the chat. Okay, the last three digits are the percent symbol, 5, 3. The percent symbol, 5, 3. Okay, so I need to tell you who for sure needs to do it. Or maybe I should say actually who for sure doesn't need to do it. There might be other people, but for sure, Dan, you don't need to do it based upon what I saw on your worksheet. Assuming you typed your name in those 3 times that I asked you to when I told you to, not later on, that doesn't count. Annie and Allie, same thing. Based on what I saw in your folders or in your whiteboards, you don't need to do the SWIC if you don't want to. By the way, this is not a penalty. If you want to try the SWIC, you'll see, oh, it's super easy, no big deal. Adam, same thing. You don't need to do SWIC if you don't want to. There might be other people, but I haven't had a chance to look at all your whiteboards. These were just the people that sent it to me well in advance of the meeting that I had time to check out their whiteboards. So I will look at your whiteboards for the people who sent it to me and see the times that you did it and how much you did and everything. But you might not want to wait. You might want to just go ahead and do the SWIC. You'll see it's super easy. The only other thing I want to talk about, let me click on, is we will not have a meeting then on Thursday. Thursday will be your test. And so, what's it say meeting for? Oh, it says meeting on the 7th, sorry. You have a meeting on after spring break. Also, I sent you an email reminding you about internet homework. The internet homework's due on the 5th, but I'm really hoping you'll get it done beforehand so you don't forget it. It's only 6, right? You only have to do 6 problems, so you might want to get it done early. Let's see. For the people who joined the meeting late, I will post a video and it will kind of go right here. So that's it. Any questions?
No, thank you.
All right. See you later. Bye.